And today I have James with me, who's the co-founder of Fireworks AI and also leads the multimedia team. So how do you see that shift where we see these agents getting better with the generative AI model? Moving forward, what are the next steps that your team is focusing on? What are the next breakthroughs that you're working towards?
Our team is focused on quality, efficiency, reliability, and ease of use, and basically pushing on all of these axes for our speech systems.
Hi everyone, welcome back to Fireside Chat with Fireworks AI. And today I have James with me, who's the co-founder of Fireworks AI and also leads the multimedia team.
Yeah.
We recently had some of our exciting audio releases around automatic speech recognition, and we wanted to chat about that and ways of building voice agents and what are some of the best practices. So, James, help me understand a little bit more about how we are seeing the Gen AI applications evolving. Because earlier we used to have a lot of text based models, and now we are seeing a shift where voice is becoming the new user experience, where people are interacting with voice, and when we do that, the primary challenge that comes is with latency and like how seamless that interaction feels like. So, with the voice based agents or voice based applications, what are some of the real world applications that you're seeing primarily right now?
Well, so voice is the most natural way that we as humans communicate. We're speaking right now,
Yeah.
right? Obviously, right? So making computer systems talk to us is a very compelling sort of proposition, right? We want to be able to interact with computer systems in a more natural way than we do today, right? Compared to typing or what have you. So we're seeing really an explosion of use cases of computers both understanding and generating a speech so that we can do useful tasks with them. For example, for understanding speech, we can talk about meeting transcription, right?
Yeah.
Or offline analytics, right? So many of you have probably used different platforms where it will listen to the conversation that's happening in the meeting.
Yeah.
It'll give you a transcript. It'll give you a nice summary, and maybe it'll distill out action items, or like if you have other some other structured like process that you work with, like for example in sales, right? Then it can also help to automate a lot of those processes just based on listening and understanding like to the conversation. Second, we see sort of conversational voice agents. So these are things that you can actually talk to. You can talk to the computer, and then the computer can actually talk back to you and engage in a natural conversation as if you were talking to a human.
Yeah.
Right? So we're seeing a lot of use cases pop up here around, for example, customer service or sales and things like that, where the computer can actually do useful work for you.
Yeah.
Right? You can ask it, right? I can ask it like, when do you open, right? Or can you place an order for a pizza or things like that, right? And then it can give you a very high accuracy, right? And fast like responses to do useful things for you.
So, James, you were talking about the voice agents, the end-to-end architectures of different models that we're using in that process, right? Why is it such a compelling problem now with the Gen AI space?
Yeah, absolutely. I'll start out by saying that making computers talk to humans in a very convincing and compelling way is a very old problem, half a century old.
Yeah.
Since the beginning of the formulation of AI as a field, this has been like one of the top problems to be solved. But it's really complex and it's an unsolved problem. And why is that, right? So the way I like to think about this is I think there's sort of like a stack of speech. So one, there's the physical layer, right? So what is speech? My vocal cords are ringing, right? Like I have air coming up through my vocal column, right? I have resonation, and then I have movement of my tongue and teeth and things like that. The articulatory features, right? That is the baseline creation of the actual like speech phenomenon in the physical world. Then my speech is transmitted over the air. It picks up echoes from the room. It picks up different noise like outside, right? And then we have the specifics about, how is the speech actually captured? Is my mic good or is my mic bad?
Yeah.
Right?
Yeah.
Does my speech go through like a very high compression codec, right? Does it go over like a telephone line, which distorts the speech? And all of this. There's all of this complexity, which means that making a computer understand speech in full generality is sort of tantamount to solving physics, right? The computer needs to be robust to all of these variations and like understand like the physical phenomena that are happening. On top of that, we have our human element. We have the linguistic or phonetic element, that linguistic or phonetic layer. So As you know, there are thousands of human languages, each of which has many, many, many different dialects, accents, variations, and even individuals have variations in how they speak. The computer system needs to be robust to that as well, which is a very kind of human-centric and potentially also like cultural problem. And then on top of this, we have the semantic layer, what I call, which is sort of, can the computer understand and do useful tasks over ideas that are expressed in language? And this is where LLMs, right, and Gen AI as a whole are really shining nowadays. So when we build speech technologies at Fireworks, we are trying to solve the first two layers to unlock that third layer, to unlock this new AI in intelligence with speech. So to summarize, I would actually say we're kind of in a same old situation where we have this problem of making computers understand and generate speech. But the new neural techniques actually allow us to do this in a way that is much higher fidelity, right? And much higher accuracy, and in a way that it can solve much more complex problems for us than we could ever do before.
So, James, some of the use cases that you mentioned, right, when it comes to customer service or drive-through, we have tried out voice bots before. Industries have tried it out. And most commonly, people just hang up because they are like, just transfer me to an agent, because it doesn't understand the queries that you're looking for. And it's very stateful, where it's like, hey, you have 4 options. And if the customer is asking for something which is not in those 4 options, it's not of any use to the customer anymore. So that used to again get rerouted to an actual human agent, because the agent, which is like automated, is not able to serve the users anymore. So how do you see that shift where we see these agents getting better with the generative AI model?
Yeah, absolutely. And like what you're talking about, the baseline of what's called the IVR, or sort of phone tree use cases, where you have a very fixed set of like options that you can go through, are what we see as sort of like, where we're moving from. With the new Gen AI advances, and especially LLMs, what we've actually seen is that sort of, at the semantic layer, I like to call it, we can actually make it so that the agents can, number one, comprehend more, right? Number two, they can reason, they can make decisions like based on natural language at the input. And then number three, they can output very convincing natural language to interact with you as a human in a way that's much better than, essentially you're stepping through like some if else statements, like as you might see like in a modern IVR system today.
Absolutely. So when we're looking at the modern voice stack, we are seeing like ASR, we have like diarization, we have LLMs in place, we have text speech. So it's a very, very complex stack that we're looking at. So each layer obviously has its own challenges. So when you are thinking about building voice agents, what are some of the best practices that you see which really helps you building this entire voice agent stack much easier?
Yeah, I can tell you where we are today and where I see us going into the future. As you mentioned today, oftentimes we'll build a layered or so-called cascaded stack. This involves a separate component for understanding the speech, transcribing that into text, putting that in an LLM's prompt, right? Dispatching the LLM to give us an answer or do some sort of like reasoning, and then taking the output from that and passing that to another system that will actually synthesize speech to respond to the human. Now, this, as you mentioned, is pretty complex, and some of the problems with this include, one, that orchestration. There's a lot of software engineering, and it's sort of like a real-time kind of like application that you have to get used to, right? Like there's an actual timeline that you're trying to schedule things to happen on. And then two, one of the challenges that I'll actually highlight from this architecture is something like what's called end of utterance detection, right? So with a modern LLM, you give it sort of a block of text, right, which is a prompt, right? Now, when you compose this with a speech understanding system, right, well, we need to make a determination once the person's done speaking, right? When can I start and kick off like that actual LLM thinking and get it working towards giving me an answer. Now, here's the problem. Conversation is fluid, right? And it's very complex, right? Conversation is not necessarily organized like a nice chat template, like you might see like in an LLM, right? So to approximate like a sort of this chat template format, we have a separate classifier that is doing end of utterance detection. And it's basically saying, right, making a guess, right, essentially, do you want an answer or not? And there's various ways of doing this. You could measure the signal power when it goes down, right? And then you have a timeout, and then it just starts yapping back at you, right? Or you could use a lightweight speech recognition model and time, hey, like, has the actual like thing that the person said changed, right? Yes or no. If it hasn't changed over a specific amount of time, they're probably done speaking, right? Or you could apply a full-on speech language model, right, to analyze the speech like in whole, right, to make that determination. But like just to highlight some of the complexity of this determination, people could use filler words, right? They could be speaking stilted like this, right? Or there could be intonation cues to indicate I'm not done speaking. Or, right, they could the turns could be of negative length. Someone could cut in and interrupt, right, one another, or even the agent. Maybe it got that determination wrong and it's interrupting the customer, but they weren't actually done speaking. So I think like the way that we see things moving is actually evolving past this cascaded like approach. How do we actually like impart full fidelity, like understanding and orchestration from speech to speech, right? So how do we make it so that number one, the whole system all the way through to like the output is aware of the flow of the conversation and can like, time its responses in a very natural way. And then number two, how do we address information loss, right? Which is sort of like if you're transcribing something into text, right? Then you lose all of that like information about like how the utterance was said, the tone of voice, right? The identity of the speaker, different maybe background like noise that might be relevant to the speaker. How do we actually engineer systems that have this full understanding of essentially the full space of physics, right? That's involved in conversation. So the cutting edge research today is really centered around end-to-end conversational speech systems, right? And like oftentimes this will involve encoding audio directly into an LLM's latent space and then decoding audio from the latent space. And in addition, there's this concept of full duplex, right? Which is where the LLM is constantly simultaneously listening and also speaking back at you. So the LLM itself can learn what is a proper conversational flow. It can learn, right, when is someone saying fillers. It can learn from the tone of voice when to respond like appropriately, right? And then it can do all of that at once from data, right? That's the main thing that we're seeing nowadays. It can learn on its own from data. And then we don't need to do any of these engineering, like we don't need to solve any of these engineering problems to like make this orchestration better.
So James, one of the biggest issues what happens with voice agents when you're going from like speech recognition to responding in speech is latency, right? When you're trying to optimize for one or the other, you're either like losing on the accuracy of the models or not responding in the right way, or you're taking too long to respond. And that becomes a challenge when you're trying to deploy this in real world applications because real users want accurate responses at the same time, like fast responses. So, what are some of the updates that we have with the latest audio release?
Yeah, so definitely. So I think there's two parts to this, right? One, as I mentioned, there's sort of this end of utterance detection, right? And improving the quality or at least the determination of like when the user's done speaking does a lot. I'd actually say that's like a high order bit in terms of how responsive does the conversational experience feel, right? And then, as I mentioned, we're moving more towards end-to-end speech-to-speech systems. So hopefully the models will learn organically how to time their responses like along the timeline here. But outside of that, once we have once we've determined that the model should respond here, then it's sort of like more of a problem of like how fast mechanically, right, does the model run, and especially at scale, right? And so the great thing about developing speech technology at Fireworks is that we actually don't need to choose between accuracy and latency. So we've got our fire attention stack, right? We've got the custom implementations of like the different kernels, right? And then all of the surrounding optimizations within the server and then in the surrounding cloud infrastructure. and co-location, on the network. So all of this together makes it so that we can run the largest, most accurate models much faster and in a much more responsive way to the customers, or like for our customers, without having to compromise on that. And the reason that this is applicable to the speech use cases is that uh, most of these technologies that are coming out for speech processing and speech generation, and also the LM in the middle, are based around this decoder-only transformer architecture. I can give you some examples. So the Whisper architecture, right? One of the most popular ASR models is actually an encoder-decoder architecture. So it uses a lot of the same self-attention, cross-attention, and sort of like mechanisms inside that we can reuse to actually run with low latency at scale. Same thing with something like TTS. So the Orpheus architecture, for example, is literally a llama. It's a llama architecture, which is sort of our bread and butter for optimization, and with some additions sprinkled on top for making it so that the LLM can predict these tokens that you can decode out into like an audio waveform. And then, obviously, in the middle, the intelligence part of your stack is an LLM, right? And all of the different tricks that we've applied to making the large-scale LLMs run fast at scale also apply here. And then, on top of that, we have tools like the Fire Optimizer platform, which you can use to actually train the model to do these agentic tasks for you. If you need it to follow instructions or make function calls to interact with your systems, you can do this all on Fireworks. It's all like together in one platform.
Makes sense. Makes sense. So, James, when you started talking about voice agents, you mentioned about several use cases that we're seeing in the industry, right? Whenever we're looking at people calling customer support bots, it is a one-on-one conversation that one person is trying to have with the bot. But as soon as we move into other real-world use cases, when it comes to meeting transcriptions or trying to find the to-do list, or even trying to analyze what's happening in a podcast, there's a lot of like these summarization tasks that we're using voice agents for. It's more than one speaker. And it's one single audio file that contains all of these different dialects, different speech tones, different like sentences that people are saying. So that is a fundamental problem when it comes to speech recognition, that how do you understand each and every different speaker? How do you differentiate it and chunk those contexts separately? So in our latest release, we have been adding into like the diarization in the speech. So can you talk a little bit more about that and some of the more industry-specific use cases that you've seen where people care about it?
Yeah, absolutely. In terms of use cases, definitely meeting transcription is one that you've talked about. Also, for example, medical scribing. There might be multiple people, the physician, there might be one or more patients, right? Or guardians in the room, right? So being able to pull these apart and like feed that downstream, annotated like to a system like an LLM to say who said what. Or even just for human like consumption in your meeting transcription, knowing who said what is super valuable. So in terms of the technical approach here, I'll start out with the problem. So the speaker diarization problem is pretty hard as well, for a lot of the same reasons that ASR in general is hard, right? You have many different like environments in which like the speech might be recorded. You have many different speakers, as you mentioned, many different languages, accents, like ways people are speaking in the moment. Like that. And then people might be speaking over each other. Again, right? Reality and conversation is not organized like nice, neat chat turns like in an LLM, right? So the techniques that are available to do this today are essentially like a optimization problem, right? It's for each given segment, like in the audio, let's find a likely assignment of like, okay, this is speaker A, this is speaker B, this is speaker C, and so on and so forth, such that this assignment is consistent, right? So speaker A talks once and then 20 minutes later they talk again, right? We should mark those like as like the same speaker. But people come and go, they talk over each other, right? Maybe someone like switched from their phone to their like the VC and their voice sounds a little different, right, on the call. This is sort of like an inherently difficult problem, right? So the modern techniques today will literally run this optimization problem. They'll split out the segments and cluster them together and find some sort of like minimal assignment of like who said what. What we've delivered is streaming diarization, right? So whereas with the existing approaches today, you have the luxury of being able to look out over the entire audio track, and then you can continually iteratively update this assignment over time. What we've delivered is actually sort of more causal, right? As the audio is coming in, like in a meeting transcription, like a live meeting transcription, let's try to figure out who said what, which is a little bit of a harder problem, right? To do. So you've sort of like assigned speakers like in the past, right? Okay, so who's speaking now, right? Figure out and make sure that's consistent with the past. This is really useful for if you, for example, analyze podcasts, right? You know who said what. If the podcast is being streamed, like this can be split out in real time. And then in the meeting transcription use case, it's also you can get insights on who said what, and then potentially live you can pass the diarized transcript down into a downstream system like an LM to make queries live to help you during the meeting, right? So this is super useful. And so we've basically done some algorithmic innovations to make this possible.
Okay. So moving forward, what are the next steps that your team is focusing on? What are the next breakthroughs that you're working towards?
Yeah, absolutely. So our team is focused on quality, efficiency, reliability, and ease of use, and basically pushing on all of these axes for our speech systems. So I would say that going into the future, you should keep an eye out for two things. One, the infrastructural releases that we have. So the speed, efficiency, and reliability of the Fireworks platform, as you know, we also are going to provide that and push that even further for the speech products that we're delivering. And then number two, we're also participating with the community and pushing on the quality aspect. As I mentioned, all of the research on end-to-end speech models or end-of-utterance detection or different new emerging TTS or ASR architectures that are coming out, we are jumping in and we are trying to contribute and push forward with the rest of the industry to make these things better, to make the conversational experience better, and to help you build better products.
That's wonderful. Well, we'll be excited to learn more about the upcoming updates. In the meantime, if you're interested to learn more about our audio release, do check out the description. We'll add the resources and the cookbooks below. If you have any questions or there are any topics that's on your mind which you would want us to talk in the next fireside chat, please make sure to drop that in the comments below. Thank you so much, James.
Thank you.